All right, so the next speaker is Rahul Ajit from Utah, who will talk about multiplier and test modules of extended Rees algebras. Please go ahead.
Thank you for the opportunity. Um, this is the only typed up version of my slide. So, okay. So I am going to talk about test modules and multiplier modules of extended Rees algebras. But before that, I want to clarify the notations. So I will be talking about local Noetherian ring of dimension greater than equals to 2 and an ideal of positive height. S will always denote the Rees algebra or the blow-up algebra given by this. Extended Rees algebra will have an extra T inverse, which means in the negative degrees, these are just copies of R, and in the non-negative degrees, this is just S. And G will denote the associated graded ring. Um, Before I go into the technical parts, I wanted to record some easy observations or the geometry behind these objects. So proj of S is the blow up along A with exceptional divisor E equals proj G. That's how S and G fits into the geometry. For the extended Rees algebra, first, I record these elementary algebraic facts that T quotiented by T inverse gives you the associated graded ring. T quotiented by T inverse minus A, where A is a non-zero element, gives back R, and localization at T inverse gives you RTT inverse, and T is flat over KT inverse. These things gives us the following geometric picture, which was used by Fulton and Macpherson very crucially in their development of intersection theory. This is what is called deformation to the normal cone, normal cone being denoted by Cy, which is peg G. The picture is the following. So Y denotes the closed subscheme inside spec R. Of course, I'm doing everything locally, but one can do all these things globally as well. And spec KT inverse is my A1. Um, and here is the picture. So this is my X cross A1. Inside that I have Y cross A1. I am blowing that up. And this is my exceptional divisor of the blow up. And the zeroth fiber is an union of these two things. One of them is the strict transform of X under this blow up, and the other one is this PCY with 1. This is the exceptional divisor of this big blow up, and they are glued along the exceptional divisor of the small blow up meaning this, or basically proj G. Okay. Um, and I found this picture in internet, so I included that as well. Okay, so this is why this is called deformation to the, so this bit, so now from this blow up, if I remove this strict transform of extruidal, then what I get is that the zeroth fiber is the normal cone and everywhere else it is just R. That is why it is called deformation to the normal cone. Okay, this is the geometry. The algebra or the algebraic reason of studying extended Rees algebra is that it makes my non-principal ideal, which I started with, which is A, principalized in the following way. So if we look at the ideal T inverse inside the extended Rees algebra, I see that the degree 0 piece is just A, and this was the principalization trick of David Rees, who introduced this algebra. And in those days, it used to be called just Rees algebra, not extended Rees, just Rees algebra. And he proved various important algebraic results using this principalization trick. I was told that in modern days, k-stability world also, Rees algebra usually means extended Rees algebra, but the grading is opposite in the sense in the negative degrees, this is just t square like that, and then the positive degrees, this is t to the -1, t to the -2 like that. But by that time I already finished writing the paper, so I will stick to this notation for now. Okay, now here is the philosophy. The philosophy is that G has a property P that is very tightly related to R, the base ring, and the Rees algebra S having the same property P. Since 1970s, commutative algebraists and algebraic geometers, including Goto, Shimoda, Trung, Heidi, Hunaka, Lippmann, Aikida, Yai, Wallermeyer, Vasconcelos, etc., proved results for P equal when the property is Gorenstein, Cohen-Macaulay, and they were in various cases, like for first from maximal ideals, then of height greater than or equals to 2, complete intersections, like that kind of, so this subject has a lot of history. And I include my this work includes the property P for rational, F rational, strongly F regular, and KLT singularities. So now let me actually define two of the main players. First, I want to define rational singularity and multiplier module. So let x comma, so x comma a was, as in my setup, just a ring. So and a is an ideal of positive height. Here I am in characteristic 0, of course, assuming that there is a log resolution. And then I define multiplier module j omega x a to the lambda, where lambda is some positive number, by this push forward, which is inside omega x. And then x a to the lambda has rational singularities if ox is quasi-isomorphic to r pi Loerster ox twiddle lambda e floor. This is in the happening in the derived category of coherent sheaves. One quick remark is that if we assume x is Cohen-Macaulay, then x a to the lambda has rational singularities if and only if the multiplier module is trivial, or the entire thing, the omega x, which means multiplier modules measures the failure of rational singularity. Okay. I want to define the character. I won't define, but I want to mention the characteristic P analogs of these singularities. So in cat 0, we have KLT singularities, and they correspond to strongly F regular in positive characteristic via reduction mod P. Also, strongly F regular honestly implies KLT. Similarly, we have rational singularity, which I defined, and they correspond to F rational singularity in positive characteristic. KLTs always imply rational in characteristic 0, or in positive characteristic for low dimensions when the characteristic is large. And under Gorenstein assumption, rational implies KLT. Exactly same story is true, that F rational implies strongly F regular under Gorenstein, and strongly F regular always implies F rational. Okay. As we defined earlier, that multiplier module measures rational.
I'm not sure if there was a question, so.
There is a question? No. Okay. So, okay, and multiplier modules measures rational singularities. Similarly, multiplier ideals measures failure of KLT singularities. Here also we have the corresponding to multiplier module something called test module, and corresponding to multiplier ideal we have test ideal, which measures failure of strongly of regular singularity, and they are related to each other by reduction mod P in some sense for a fixed lambda. Okay. Now I want to mention, or I now I am ready to mention my main theorems. So main theorems have several parts. So first, I want to mention a technical result. This technical step was one of the main key steps in our positive characteristic proof. So this says the canonical module of extended Rees algebra. So we describe canonical module completely, or not completely, in the positive degree completely. So we prove that the positive part of the canonical module matches with the canonical module of the Rees algebra, which was computed by Hyrie, Smith, or Hochster, Roberts, etc., and other mathematicians by this geometric object. So that's how the positive degree part of the canonical module of the extended Rees algebra looks like. On the other hand, in the negative degrees, if we go sufficiently negative, then they all become just omega r. When we assume that S is Cohen-Macaulay, that is algebra is Cohen-Macaulay, then this is true for all non-negative degrees. I don't need to pick it. So M0 is equals to 0 in that case. And our proof is completely characteristic free. We basically study the top local cohomologies, or the local cohomologies of S and T. And this gives us, so this particular technical result actually reproves many of the works from 70s about relating Cohen-Macaulayness or Gorensteinness of these algebras, and hence they have some applications, but I did not record them. I will go to the main theorems actually. So this main theorem has two parts. One part is a characteristic 0 and the other part is the characteristic P. The characteristic P part is joined with Hunter-Simper, and but the proofs are very different. But before I explain the theorems, I should cite there were lots of this similar kind of decompositions appeared in the literature under various setup. For example, Hara Watanabe Yoshida, Hyrie, Karen Smith, Joseph Lipman, Kumini Kotal, Budur Mustatsa Saito, Hara Yoshida, and Budur Saito. And today morning, I learned from Bradley Dirks also. So now let me explain what these decompositions say. So in characteristic 0, the multiplier module of extended Rees algebra decomposes like that, where I am following the notation that when n plus lambda is less than equals to 0, this is just R. Okay. And the multiplier module of the Rees algebra looks like this, basically the positive part of this decomposition. And the cool thing is the degree 0 piece is computing multiplier module downstairs. So in positive characteristic, if I assume R is reduced because I need the existence of a strong test element, then exactly similar decomposition works. But the proofs are, as I said, very different. The characteristic 0 proofs are extremely geometric, or I'm doing various story computations. And on the other hand, positive characteristic, I'm using a result of Schwed and Tucker to compute these things carefully using this canonical module decomposition formula. Okay. Any question about these decompositions before I go to show some applications? Okay. So here are a sample of applications we can do. So the first thing is we can answer a conjecture or a generalization of conjecture of Hara Watanabe Yoshida from 2002, where they asked that if T is F rational, does that imply that R and S are F rational? They assume they were in the M primary setup, where it was in a very different approach proved by Kumini and Cole. but we could prove it for any ideal of positive height, and our proof basically just follows from these decompositions. If we put lambda equals 0 here, like in all three, lambda equals 0, then we immediately see that this thing being trivial immediately implies these are trivial. We need to check Cohen-Macaulayn's in a different with a different argument. And similarly, we are given Hara Watanabe Yoshida proved this direction, the green direction, that if R and S are f rational, then T is f rational. Again, we get that from these decompositions in some sense, because f rational implies Cohen-Macaulay. And also note that if G is f rational, then because G is T quotiented by T inverse, by the deformation property of f rationality or rationality, we get if G is f rational, that implies T is f rational, which implies R and S are as well by their conjecture. And that was their motivation to phrase this conjecture. And similarly, in a separate paper, Hara, Watan, and Yoshida studied similar questions for rational singularity. We get those things also from the multiplier module decompositions. Okay. Another application is the discreteness and rationality and periodicity of jumping numbers. What that means is that assuming the principal ideal case, so the point is that this point number 3, that even if I start with a non-principal ideal downstairs, I can honestly principalize it, and then the degree 0 piece computes it, which means wherever this thing jumps, the entire thing must jump, and I know that these things have discrete and rational jumping numbers. And that gives us a quick proof of discreteness and rationality of f jumping numbers. Similarly, via Skoda, for example, we know that T inverse to the lambda plus 1 is just T inverse times that thing, which gives us in some sense the periodicity results of these jumping numbers for infinitely many natural numbers. And if we can prove these decompositions for in mixed characteristic, that will tell us that if we can prove discreteness and rationality of plus pure thresholds, for example, in principal ideal case, then we immediately get the same for non-principal ideal cases. And there are some applications of inversion of adjunctions as well. This was, for example, done in MSTWW. This is Marsh, Wade, Tucker, Waldron, Witazek in their joint ideal paper. And the other computer application is that now we have a Macaulay 2 package which can compute test ideals for non-principal ideals. Before that, it could only compute the principal ideals or test ideals for principal ideals, but via this trick, one can do the same for non-principal ideals. And I want to mention a couple of future directions. So there we did it for Rees algebras, but there is a way to do all these things for multi-Rees algebras or for filtrations. Heidi and his co-author studied these things, but the hope is that this will give us various algebraic properties of multiplier ideas, like sum of the two ideals or products or this kind of properties. And the other thing is Bernstein-Sato theory. This entire decomposition, this decomposition for multiplier ideals when R was smooth, was proved by Budur Mustatsa Saito and using V filtrations. And today morning, Brad Dirks told me that he knows how to. He sent me the paper of how to proving this in the singular cases as well, and developed I did not read that paper carefully, but I think he developed a theory of Bernstein-Sato polynomials also using this. So That's all I have to say. I'll stop here.
Thank you very much. Any questions for Rahul? So I have one question. So for these results regarding discreteness, rationality, so what are your assumptions? So what about the ambient variety or?
Ah, so I have proved all these results for test modules, right? So to
Mhm.
go to from test module to test ideal, I need my R to be Gorenstein.
I see.
That's how I will relate test module to test ideal, and hence my assumption is Gorenstein. I mean, of course, otherwise there's a strong suspicion that there is a counterexample, right? That of the rationality. Yeah,
I see. I see.
yeah. But for test modules or multiplier modules, I don't need the
Don't need
Gorenstein.
any assumption. I see. Could you say also one word about what sort of inversion of a junction you get?
So I did not prove these things, but when G is reduced, then basically quotienting by T inverse behaves very well with respect to computing multiplier modules or test modules. You can compute omega G, canonical module of G, pretty easily. And I think in the M primary case, Marshwood, Tucker, Waldron, and Witazek use this exactly for this reason. But I did not do this. Yeah.
I see. Thank you.
Yeah. But the problem is that G is not usually reduced.
Other questions or comments?